All right, in this video, we are going to continue our discussion on sugars. And here is where we left off on Monday, looking at glucose. And the important things to remember is how do you tell D sugar? It's the last OH. How do you determine stereoisomers to the power of chiral centers? And what's an epimer? An epimer is only different at one chiral carbon. Everything else is the same. So here we have our first question. For these, please pause the video and try it before you look for the answer. So how many stereoisomers are possible for keto-pentose? So the first thing we need to do is simply write down what a keto-pentose looks like. Right? So 1, 2, 3, 4, 5. So there's our pentose. Remember, pentose means 5. Keto means the C double bond O is on the second carbon. Then we just fill it in. And you see we have 2 chiral centers. So the possible number of stereoisomers are 2. It's always 2 raised to the power of chiral centers. 2 raised to the power 2 is 4. We do the same thing for ketohexose. So figure that out, come back, and let's take a look at this. So there's our hexose. Three chiral centers, 2 to the power of 3 is 8. And then our ketoheptatose. So hopefully you paused it, came back, and are looking at the answer now that you have figured it out. So there's our heptose, ketoheptose. So 1, 2, 3, 4 to the power of 4, which is 16. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So that is how you find stereoisomers for your sugars. Next, we're going to look at epimers. So if you don't know what an epimer is before you answer this question, go back to the notes and figure it out. Then come back to this slide or go back to this part of the video, look at it. And now we're going to discuss the answer. So please make sure you have figured this out on your own before listening to me do it. So we want to know sorbose and psychose. So sorbose is right here. Psychose is right here. So right, 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 left, right, right. So they are epimers because you are only different at this chiral carbon. Every other chiral carbon is facing the same way. So yes, they are. Then we have sorbose and fructose. Let's look at sorbose and fructose. All right. So sorbose is here, fructose is here, right, right, left, right, right, left. So you have 2 carbons that are different. So these are not epimers. Epimer is only 1 chiral carbon that is different. Erythros and arabinose. So let's take a look. There's arabinose. And erythros is up here. Automatically, they are not because they are a different amount of carbon. So they're a different amount of carbons. By definition, they can't be epimers. D and L fructose. Right, think about this. This one's a little tricky. So we have D fructose. Let me draw L fructose for you. All right. So hopefully you remember what I said about D and L. The last chiral carbon, the direction tells you if you're D or L. If you're pointing to the right, D. Pointing to the left, L. And my experience asking this question, people will say true because that's D or an L. But the thing that decides what sugar is which is all of the carbons. So for example, in D fructose, you have a carbon pointing to the left, then right, right. So the last two are pointing in the same direction. So that's what we have to do in L fructose as well, right? The last two OHs pointing in the same direction. The top one isn't, right? So L and D are not. So the big takeaway here is if you go from L to D, every other OH swaps, so you get the same pattern. So for example, D ribose are all to the right. L ribose would be all to the left, all the OHs. Okay, arabinose and ribose. So here's ribose, here's arabinose, right, 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 left, right. They differ in exactly one chiral carbon. And I believe this is our last one, ribose and ribulose. And they are not. One's an aldose, one is a ketone. So by definition, they cannot be epimers, right? So not only does it have to have the same number of sugars, they have to be in the same category. They have to be both aldehydes or they have to be both ketoses to be epimers. All right, so we have been looking at sugars in the linear form. However, inside the cell, the majority of the time, the sugar is in the cyclic form. That is, it's in a circle. And two major cyclic forms exist, depending on how many atoms are in the ring. We have a pyranose and we have a furanose. So here's the pyranose, 1, 2, 3, 4, 5, 6, while furanose has 1, 2, 3, 4, 5, right? So depending on how many carbons, or sorry, how many atoms you have in your ring, you're either a pyranose or a furanose. Now, the reaction that go from the linear form to the cyclic form is a reaction you should have seen in organic chemistry, where if you combined an alcohol and a ketone together, what happens, and bring back your electrons, you have your alcohol attack the carbonyl carbon, forcing this double bond to become a single bond. And then this oxygen, this carbonyl carbon, will take a hydrogen from water, and you get what's called a hemiketal, right? So this is the reaction that happens inside the body, and to make a linear sugar to cyclic. For us, our alcohol is always going to be the last chiral carbon, and it's going to attack the only C double bond O inside the sugar. All right, so here's glucose going to glucopyranose. So this is glucopyranose is like the chemical name. We saw call that glucose. And this, as you can see by this arrow, the linear form and the cyclic form both exist in your body, right? When glucose is by itself, it will constantly switch back and forth between these two forms. I don't remember the exact percentages in my mind. I want to say like 70% of the time it'll be cyclic, roughly 30% of the time it'll be linear. But just be sure you know how this reaction goes, that you can do this yourself, right? And so that's how we form a cyclic sugar. And on the bottom here, we have the same reaction, but for a fructose to make our furanose. Now, if you noticed, when we looked at the glucopyranose, I didn't mention it, but if you were looking at the name, you would have saw it was called beta D glucopyranose, right? That's because the alcohol that's doing the attack is part of a chiral carbon. So when we do this attack, there's actually two different glucoses that can form. We call them alpha or beta. The reason for this is because around this carbonyl carbon, you have a carbon-carbon single bond. If you remember from organic chemistry, single bonds, molecules that are part of single bonds are rotating. So you have all across all of these single bonds, you have rotation. And depending where you are in the rotation when you have this attack, you'll get one of two forms. You'll get either the alpha form of your pyranose or the beta form of the pyranose. And the way we tell what form we're in is by the former carbonyl carbon, right? So carbon 1 is the carbonyl carbon. And I should have mentioned this earlier. I'll do that now. Take a break from this idea and just mention the naming scheme of carbons. So in the linear form for aldehydes, the carbonyl carbon is number 1. Then you just go down the list, 1, 2, 3, 4, 5, 6. For ketones, the carbon above the ketone is 1. Then it's 1, 2, 3, 4, all the way down. And so when we cyclize, when we form this ring, we keep the same carbon numbering. So the carbonyl carbon is still number 1. 1, 2, 3, 4, 5, 6. And depending which way this carbonyl carbon is pointing, we'll have alpha or beta. And what you need to look for is the position of this alcohol group of your former carbonyl carbon. So for example, this OH is pointing down. We compare that to carbon 6. Carbon 6 is pointing above the ring. So you have the alcohol group on carbon 1 pointing down. The CH2OH on your 6 carbon pointing up. They are in pointing opposite directions. So we call that an alpha sugar. While in the beta form, the OH is pointing up, the CH2OH is pointing up. They're both pointing in the same direction. So we call that a beta sugar. And some other terminology for you. This former carbonyl carbon in the ring form, we call that the anomeric carbon. So anytime I'm talking about the anomeric carbon, which I will do quite a bit moving on, I'm talking about the former carbonyl carbon that's in our ring. And it's the anomeric carbon that is determining alpha or beta for us. So I have a bunch of examples here to make sure you're comfortable with this idea. Again, don't wait for me to just give you the answer while think about it. You're only cheating yourself. Pause, look at this and try to answer it. All right, so here is our first sugar. And you have to find the anomeric carbon first. the anomeric carbon, it will be the only carbon that's connected to two oxygens. So it's always going to be the carbon that's connected to the oxygen in the ring, because this was the former OH that did the attack. So you have two choices because you have two carbons attached to that ring. You're looking for the carbon that's also attached to an OH. That is how you find the anomeric carbon super fast. You find your oxygen, you look to the right or to the left. Whatever one is connected to an alcohol group is anomeric. So here we have our OH pointing down. Here we have our CH2 OH pointing up. That's alpha. Here's our second example. Let's try it out. Find the anomeric carbon, look where it's pointing, compare that CH2OH. This is pointing up. This is pointing up. That's beta for both directions, or both pointing in the same direction. All right, here's your first 5-membered ring, but it's the same idea. Take a minute and try to do that. And welcome back. I hope you did pause, or at least you are able to figure it out and you're just not waiting for me again. So here's our anomeric carbon connected to oxygens, pointing up, pointing up. So that is beta. All right, one more for us. Here's anomeric because it's connected to two oxygen, pointing down. Here we are pointing up, alpha, opposite directions. And the sugars in your body, they can be modified in a lot of different ways. So we're gonna look at some of these modifications. So what I would like for you to take from this slide is be able to know the different modifications, be able to look at them and name the modification, or if I give you the modification, be able to do the correct sugar. So first are deoxy sugars, right? A deoxy sugar is anytime one of the OHs has been removed and replaced with a hydrogen, right? So we know this from DNA. DNA is deoxyribose because at position 2 here, and remember our naming scheme is anomerics 1, then you just go around away from the oxygen. Carbon number 2 here is hydrogen. And you can also have this at different positions. So we have learned from biology, DNA is 2', but here we have it on a different carbon. So carbon 1, 2, 3, 4, 5, 6. Here, carbon 6 has had their OH removed. So that's also deoxy. Now let's look at our aldonic and uronic acids. So aldonic acid is that you take your C double bond O, you make it a carboxylic acid. So normally, you know, it looks like 1, 2, 3, I have to count my right number of hydrogens there. So normally our aldehyde will look like this, but if you attach an alcohol group, remember this is a carboxylic acid, and our name is gluconic acid. This for glucose. So this is an aldonic acid. And the naming scheme is you just add onic acid to the name. So instead of glucose, gluconic. Your uronic acid is that you take the last group and you make that C double bond OOH. So you're taking your alcohol and changing that to carboxylic acid. So this is called a uronic acid. And again, we just add the word uronic acid to it to make glucuronic acid. Our next type of modifications are called the alditols. An alditol is where you take the C double bond O and you reduce it to an OH. And so this can be an aldose or a ketose, right? And the naming schemes is you just add itol to the end of the name, or all rather, I guess. So an alditol, you don't have C double bond O anymore, it's OH. And then our aminos modifications is you just take one of the OHs and you put an amine group there instead. So that one's easy to look for, NH2. We're going to talk about the significance of that in a later lecture. But from this slide, make sure you know our 5 classes. Make sure you can spot a deoxy, an aldonic, uronic, an alditol, and an amino sugar. Flashcards might be helpful for this, as this is memorization. All right, so now let's talk about how we connect sugars to one another. And the way that we connect a sugar to another sugar, or really anything, is called a glycosidic bond, where you have your anomeric carbon being bonded to something else. And that something else is always going to be an oxygen or a nitrogen. And we call those O glycosidic bonds or N glycosidic bonds. And believe it or not, we have already looked at this semester in our nucleotides. So hopefully now you can spot an anomeric carbon. So here we have our anomeric carbons forming a covalent bond to our bases to form our N glycosidic bonds. And glycosidic bonds are relatively stable. Think of them like peptide bonds. So they're covalent and they don't break easily, right? So it's a way for a sugar to be connected to something that's relatively permanent. They can break down. All covalent bonds can break down, but it's kind of like super glue. It's hard to do. Now, if we form a glycosidic bond between 2 sugars, and those 2 sugars are connected by a bond, we call that a disaccharide. So di means 2, saccharide means sugar, so this is 2 sugar. And if we connect sugars, we get more special naming. If the anomeric carbon of our is connected by a glycosidic bond, so here, let me get a different color. And I guess I should, so the ring, it's like that. Here we're connecting 2 sugars together. Both of them are, this glycosidic bond is connected to the anomeric carbons of both sugars. Therefore, we call this non-reducing. And what this non-reducing means is that these sugars can no longer be linear. Because remember, when we were talking about glucose cyclizing on a previous page here, we said, okay, glucose can be either cyclic or it can be linear, because we can form that hemiacetal or we can reverse it. And if what I'm saying right now isn't ringing any bells, go back to that slide, go back to that part of the video, review it, so you know what I'm talking about. Just don't go on and say, yeah, I'm going to learn it later. Go back, review what I'm talking about, and come back now. All right. So if our anomeric carbon is in a covalent bond, it can no longer form the linear version. It is stuck being cyclic. So if you have a disaccharide and both of your anomeric carbons are in a glycosidic bond, we call that non-reducing. If one anomeric carbon is free, so let me draw that So I just put a circle across our anomeric carbons. Remember, we're looking for carbon connected to 2 oxygens. And I did a pretty poor job of drawing my second sugar. Let me just rectify that. The OH should probably be over here, so I can clearly show you that it's not part of the ring. There we go. So this is called reducing, linear, because the second carbon here, the anomeric carbon is not in an extra bond. So that means this sugar is free to revert to the linear form that we already talked about. If one carbon can go back to the linear form, we call that a reducing sugar. So this is a reducing disaccharide. Right, so we have some practice on this. So take some moments, figure out if you're looking at reducing or non-reducing sugars here. Right, so how you want to solve this is you want to find the anomeric carbons, carbon connected to 2 oxygens. Anomeric, anomeric, both in a glycosidic bond, non-reducing. How about this one? All right, so anomeric, anomeric, reducing. This anomeric carbon on the right is not in a glycosidic bond, so this can become linear again. Therefore, we call this a reducing sugar. And here is another one. And if we look, anomeric, anomeric, this is reducing, because the second anomeric carbon is not in a glycosidic bond. And then our third one. So take a second for this one, or our fourth one rather. Anomeric, not in glycosidic bond, so reducing. So all sugars by themselves are reducing by definition. Right, and I'm just going to do a little bit more of another slideshow to try and catch up here, which would be this one. All right, so I'm just going to talk about disaccharides here. So I'm just going to go to problem 1. All right, so we talked about disaccharides just previously, and let's talk about the naming schemes of disaccharides. All right, so hopefully from the previous PowerPoint, you have an idea what alpha beta means. Now, when 2 sugars are connected by a glycosidic bond, we have to name that bond. And what you do is you just simply name the carbons that are connected by the glycosidic bond. If an anomeric carbon is in the bond, you have to tell me, is it alpha or beta? And let me start this, because every single year, and I guarantee it's going to happen again, people always say alpha and beta when it's not necessary. You only say alpha or beta if it's the anomeric carbon in a glycosidic bond. So let's look at lactose. So first, we have our anomeric carbon in a bond, right? Because it's 2 oxygens. And our numbering scheme says this is carbon 1, right? So first you name, if you find out if it's an anomeric carbon in our bond. If it is, you tell me if that anomeric carbon is alpha or beta. So here you can see the bond is going up. It goes up and then over. So that means it's pointing up. If we were looking at it pointing down, the bond would look like that. So it will tell you the direction. We compare that to the CH2OH, that's pointing up. So they're both going in the same direction. That's 1 beta, or rather it's beta 1. Then we see what is connected to in the other sugar. 1, 2, 3, 4. This is beta 1, 4. This glycosidic bond is called beta 1, 4 because it's connected to the 4th carbon on the sugar. Note, I did not call that beta 1, beta 4. The anomeric carbon is not in this bond, so I do not care what it is. And I don't care because this is a reducing sugar. This glucose can open up, and this beta, when it recloses, could go to alpha, right? So this can become linear and then cyclize again, changing this. So there's no point in naming it because we don't know what it is. However, galactose over here is in a bond. It can never open up again. So the beta is set. It is set in its ways. So that's beta. So sucrose, here we have an anomeric carbon and it's alpha. So that's carbon 1, pointed down, pointed up. So that's alpha 1. Here we have carbon 2 being the anomeric carbon, right? This is the first time we've run into this, but fructose is a ketone. It's a hexaketone. So we have our cyclization like that. So carbon 1, then 2, 3, 4, 5, 6. So we compare which way was the O2 on carbon 2 pointing. That's pointing down. Which way is the CH2OH on carbon 6 pointing? That's also pointing down, both in the same direction, alpha 1, beta 2. Here, both of our anomeric carbons are in a glycosidic bond, so we name both. All right, here's a good amount of practice for you. 5 problems. I cannot emphasize enough. Pause it, try it, come back. Waiting for the answer will not teach you this. You have to struggle. So I'm going to go over the answers right now. So if you haven't done it yet, please pause it now. Right. So our glycosidic bond. So between these 2 carbons. This one's anomeric because it's combined to 2 oxygens. Pointing down, pointed up. Apologize for the dogs. All right. So we are pointing in opposite directions. So that's alpha. This is carbon 1. So this is alpha 1. Then 1, 2, 3, 4. So this is alpha 1, 4. All right. So let's look at beta now. So here we do have an anomeric carbon. Pointed up, pointed up. So they're both pointing in the same direction. So this is beta 1. Then we have to find the other anomeric carbon. Again, we're looking for the carbon with 2 oxygens right here. Oxygen, oxygen. So this is carbon 1. Then we just go around numbering the carbons. 2, 3, 4. So this is beta 1, 4. For C, here, this is anomeric, our first one. So pointing up, beta 1. Then here's our anomeric because it's combined to 2 oxygens. So this is beta 1, 2. And D, so we have an oxygen here. So that's anomeric. And our anomeric is right here. So pointing down, pointing up. So that's alpha 1 because they're opposite directions. Here's the tricky part for the second one, 5-member ring. This is showing another carbon. So this comes back to our organic chemistry where we don't write down carbons, but we use lines as shown. So this is actually carbon 1, 2, 3, 4, 5, 6. So this is a rare alpha 1, 6. And then in E, this is also anomeric. All right, so this is going away from us. So remember, thin line is away from us. Thick line means towards us. And our 6 carbon is thick line, so it's going towards us. So this is opposite. So that's alpha 1. And here I'm testing your naming scheme of linear. So this is 1, 2, 3, alpha 1, 3. All right. So hopefully you got those. If not, please send me emails. And I apologize. I am going to be late with emails probably this whole week. Hopefully by the weekend, hopefully by Friday, I can be back in class. If not, I will try to reply to you as soon as I can. Be aware you might be getting emails from me like at 2 a.m. It's whenever I have a spare moment, I will try to get back to you as best as I can. I apologize again for not being there. I wish I was there. But yeah, I hope to see you all soon. Let me know if you have questions. I'll post the homework on to give you more practice. And hopefully you have a good rest of your day. And take care, everybody.